In this video, I'll do some experiment to try to explain a little bit about the capacitor ESR. The ESR is something we call that equivalent serial resistance in the capacitor. As in the real world, we never have a capacitor has pure only capacitance. It's always something else. This is the equivalent diagram for the real world capacitor. This C over here is ideal capacitor, only have pure capacitance. And this RL is the leakage resistance. When the circuit passes through this circuit, this leakage guy will have some circuit pass through that, bypass the C. And there is another one called ESR, equivalent series resistance. When the current passes through this circuit, the voltage will drop in the C and the ESR. So similar to a resistor who is serial with the capacitor. So that is one of the equivalent series inductor, but we are not talking about this thing today. The ESR depends on the temperature and frequency of the signal also. So it's very difficult to accurately measure the ESR. I'm not trying to do an experiment to test how big is the value of the ESR in a capacitor, but more of that I'll try to understand what is ESR. Let's build a circuit like this. This one is a C, it's a capacitor. And this R, I put the 5.1K resistor here. I pretend this 5.1K resistor is the ESR, but definitely not. If a resistor or a capacitor have that big ESR, is not going to be able to use it. And then we feed a 1 kHz sine wave to this circuit, and we are using the oscilloscope to see what happens when this AC signal runs through this circuit. This is the device we set up today. A lot of stuff over here, but actually it's quite simple. A signal generator feed 1000 Hz sine wave into this device. And this connector is the over here. And this is a resistor. The resistor here, 5.1K. And these two connect to the capacitor here. The capacitor. And these are the lead for the scope. Let's take a look what is showing in the scope. Let me take off the lead connect to the capacitor. Now we see the 1000 Hz sine wave. This one is from the signal generator. I connect the channel 2 to the capacitor. We see two waveforms in the scope. The yellow line is the one from here. And the blue line is connected to here, the capacitor. And what this waveform mean to us? First of all, we need to understand one thing here is in this serial circuit, R and C have the same current. The current in this circuit will be the same in every component. It doesn't matter the value, how big the current, or the phase. The value and the phase in this serial circuit, they're going to be the same. And the R and the C, they have the same current. We know the serial circuit have the same current, but what that yellow thing and the blue thing measure right now? This yellow thing is measure the voltage of the input, and this the blue is measure the voltage of the capacitor. If we simplify that in this diagram, the yellow line is the voltage in this input, channel input. It includes the C and the R together. It's a full voltage. The blue line is measure the voltage in the capacitor, only the capacitor. With the signal feeding to the device, right now I'm gonna go replace the capacitor with a resistor to see what's gonna happen. Now we see the blue waveform merge together with the yellow waveform. What did tell us? In the circuit with a pure resistor, the current flows through the circuit. It doesn't matter if it's DC or AC. The voltage over here will equal the voltage in two resistors add together. And they are not related to any, like a frequency or any. The value and the phase of the voltage in these two resistors will be exactly the same. That's what we are seeing over here. Yeah, sure. It never be exactly right. Real world never be pure. But we assume this is pure resistor. So now we see the waveform merge together. Because there's no phase difference for the voltage in two resistors. Yeah, let me move down to see what we have in the circuit. This is the resistor we are testing in the channel 2, and this is the resistor we tested in channel 1. And the signal is coming here and going through here. Both are resistor. Now, let's place the resistor with the capacitor. And we see the blue line shift to the right. That means something. In the RC circuit, when we feed AC signal to that, the voltage in the capacitor and the voltage on the resistor, they're not in the same phase. They're not match each other here. They have a shift. And what is that? What that blue light shift mean to us? Let's go back to the pure resistor. This pure resistor current flows through the series circuit. If we only calculate the value, we're going to have a Vy equal V1 plus V2. If we also calculate the direction, the vector, then the Vy will equal V1 plus V2. And V1 and V2 have the same direction. They have nothing different. So this equation is exactly the same as this equation. So we don't need to do the vector at all in here. But in the RC circuit, it's not like that. The Vy over here, it's not equal the value of Vr plus Vc. It is vector plus. What does vector mean? In this circuit, this is the resistor. The resistor, it doesn't change the direction of the vector. So the Vr will go like this way, flat, same as the signal direction. But the Vc, we know Vc have a 90 degree, the vector is 90 degree negative to the Vr. So this make this equation not the same as the pure resistor circuit. Let's review the capacitor charge waveform. We feed the square waveform to the capacitor. In the beginning, when the waveform voltage is 0, capacitor also is empty, is 0. And by the time the waveform voltage is going up, the voltage is going up very sharp, you see, immediately going up to top of the full voltage. But you see the capacitor is charged slowly. The voltage rises up very slow, eventually catch up. So that means the capacitor voltage is behind the voltage of the signal, because this is a series current. So the current in the signal and the capacitor is the same. So we can say the capacitor voltage is behind the current. The phase is behind the current. Yeah, why this happen? We can take a real world example. Like we have a water container. This container has certain volume. When you pour the water into that container, it can fill up the container, but the water level will going up slowly, not immediately full. So that water level we can compare to this capacitor voltage. When we pour the water into the container, that is similar to the current is charging the capacitor. And this is the vector of the capacitor phase. The current lead the voltage 90 degree. Is that 90 degree? It is ideal wall. The 90 degree is the ideal wall. When we are in the ideal situation, the capacitor have a current lead 90 degree of the voltage. And we put these two things together. You see, just now I turn this thing rotation. This the current direction. This the voltage direction. I put it this way, too easy to compare to our diagram, our equipment. So by that, what gonna affect the waveform is like this. When we are in the capacitor in AC circuit, this line, this is the I. Don't worry about this. We are not going to do this thing. This is the I, the current in the circuit. That current is the same. You see, that come over here. You see the current flows through this circuit, AC, right? The current will be the same to these two things. So this is the current waveform. When the current going to the top, the VC, this is the voltage of the capacitor. It just start charging. It go all the way up to here, and then the current going to zero. It reach to the top one, to the top of the voltage. And when that current go to the opposite AC, it's always like this, right? AC. When the AC current go to the reverse, go the other way, and the capacitor will start to discharge because the current go the other way. So the positive and negative lead is reversed. So this thing gonna go discharge to zero and charge to the other direction. Start to charge to the other direction. You go to the negative, right? And then when the AC current go to the right direction, it start to discharge and charge again. This is the waveform to describe the voltage of the capacitor and the current in the RC circuit relationship. Now, after we read this, let me put it in the middle. So that this is 90 degrees, this is 0. But we removed it. It's not like that, right? It's not like that. This is in the 0. This is not in the maximum. It's not like the thing you show here. That's what. This is ideal capacitor. The current and the voltage have 90 degree difference. And this is not an ideal capacitor. This is something like this, like this. So in this one, we have a 5.1K resistor serial to the capacitor. So now the capacitor with the resistor in the circuit. Then we can see this shift is not 90 degrees. It starts to make some sense. The ESR start to kick in. Look at this Victor picture. We got VC here, is the blue line. We got VR here, it is the resistor. So this is the one we measure in the yellow line, over here. And this is the one of the blue line. And what is that yellow line mean to us? The yellow line is the thing we measure from the signal input, over here. It's the whole thing. These two plus each other, add together. These two add together. So that add together is not just simple value add. It is the vector add. See that? Vy equal VR at the VC, VR at the VC. It's a vector adding. In the ideal world, we are saying we have the capacitor have 90 degrees of the I, right? The VC will be 90 degrees of the I. So that's ideal. And it is the capacitor design and the circuit design, everything design is focused on that. We supposed to have a 90 degree VC and with the R, with the I, that's the ideal. But somehow something kick in here. There's a R over here. What that R is? That R is this guy. In our test circuit, this R is the 5.1K we added to the circuit. In the real amplifier or real unit, this R is something we call it ESR. This is the ESR in the capacitor, inside the capacitor. So this ESR added to here, it make this VC and that VR add together. It's not 90 degrees to this I anymore. It becomes this way. See that? Become this. And what that means? If this R is very small over here, and this triangle gonna be like this. So this is the yellow line. That is the yellow line, VC. It will be very, very close to the ideal wall, 90 degrees. But if this VR is get bigger, and this will be shift from 90 degrees up to here, right? Up to here. And there is an angle here. This angle here. This angle is something, one of the parameter in the standard of the capacitor. Now we see what is ESR. Let's get some information from one of the website. I usually buy my capacitor from that website. Personally, I like Nichicon capacitor. I just stick in that manufacturer and blend. It's easy to find the parts I want. Let's see what is this mean. If we got a capacitor to do the recap, and they always suggesting you to using the good quality audio grade gold or what kind of that kind of a tone to describe what is the capacitor is premium for what is the section of the circuit. Now we are talking about the signal circuit. Signal, not the power supply. When you go to the signal circuit, if you find a blend UFW in the Nichicon, you see this diagram? They told you UFW is good, but UFG is better than UFW. How bad? How good? How better? Personally, my ear probably not be able to identify that, but I believe Nichicon is a very good reputation manufacturer. If they say good, they do have something there, not just like put it in the label and they trick your money. But in the UFW, there's one line over here, leakage current. And the other line is tangent of loss angle, tangent theta. Let's zoom into that thing to see what it's talking about. I'm not sure it's focused good. See that tangent of loss angle. See, go to the right. I will focus on that 50. See that 50? 50 volt capacitor. The rating voltage is 50. The tangent theta is 0.12. 0.12. So 63 is 0.1 and 100 volt is 0.08. What that mean to us? I might not know, but based on what they tell me, there is another one better than that. It's UFG. Let me see the UFG. This is the UFG. That's the one they said better than the UFW. Okay, let's also read there is a leakage current here. We're not talking about that right now. Tangent of loss angle. Right? Tangent theta. We also move to the 50. I think we are interested about the 50. Let's see how much there. 50 is 0.1. Go back to the vector of the capacitor. What is the ESR now. Let's introduce one of the new term, XC. We call it reactant. What's a reactant? It's the 1 over 2 pi Fc. 2 pi is 2 times 3.14. F is the frequency of the circuit. Now we're using 1000 in our experiment, but in the real world, it's whatever frequency you have. C is the capacitance of that label of the capacitor. Now, this XC, what the XC equivalent to the resistor. In the resistor, we have a resistance like 1 ohm, 1 k ohm, 10 k ohm. In the capacitor, we have reactance. It's similar to the resistance. Now, when we say VR and VC, go up a little bit. When we say VR and VC, what's VR? VR is the voltage drop in the resistor. VC is the voltage drop in the capacitor. VR equal I times R. I times R without any direction and phase change. It's just all the way to there. VC is the reactant times the I times the circuit, the current. Because in the serial circuit, current is the same, phase is the same, value is the same. So these two come together. If we put it in this equation, then we can get the value of this, right? Value of the total something called voltage. But now we're not doing the value, we are doing the vector. XC caused the VC drop. This is the capacitance designed for. We don't want to change it. It's designed to this VC. And this is the capacitor ESR. This guy is not the manufacturer wanted, but they cannot avoid it. Then what is a good capacitor? A good capacitor based on the niche control R is what? UFG is better than UFW. And UFW have 50 volt capacitor have 0.12. And UFG 50 volt capacitor have 0.10. That's a tangent theta. What's tangent theta? Tangent theta is this. Theta. This lag divided by this lag is tangent theta. CD divided by VC is tangent theta. If this one smaller, the capacitor is better, then we can say if VR is smaller and VC is greater, and then it's a good capacitor. That means what? This thing shorter. And this one, it is capacitor. You cannot make it longer. It's not supposed to be longer. So this thing is not changing. If this one shorter, and then the triangle like that, right? This rectangle going to become like this. So this is a better capacitor than this one. And yeah, if it's a new capacitor, you go to the manufacturer's website, you get a datasheet, you find a good one, and you compare the price, the cost, and you get the one good for your application. Okay, that's good. But when you get an old equipment, vintage equipment, then all of a sudden you see a lot of capacitor inside. And those capacitors out there for decades, sometimes 25 years, sometimes 35 years, or even 40 years. Those capacitors get aging. When they get aging, the inside of the capacitor may be dried out, and also the material inside break down or whatever. And then there's one thing can change is what? The ESR will getting bigger, will grow. And also sometimes they say the capacitor lost the capacitance. What that mean? If you lost capacitance, mean this thing gets shorter and grows by ESR. I mean this one get longer. Then in this equation, this thing get bigger and this one gets smaller, and this tension theta gonna become bigger. So based on what Nietzsche can tell us, this capacitor go downward. Go downward. And what is the threshold to replace that? I don't know. But something out there for 40 years, if you trust that, you read the label or you read the warranty or whatever the standard for the website, they never told you the capacitor can using for 40 years. Definitely in the website of Mouser, they have the data sheet of a lot of capacitor, and they also have the life cycle or what kind of storage time or something like that. We can reference to that. Let's say we have a coupling capacitor which connect the input signal to our amplifier, the power amplifier signal. We're supposed to have one very ideal capacitor here. And then when the signal passes in, it doesn't matter what frequency it is, what is the volume. The signal will be exactly copied into our amplifier. That's the ideal one. But now, we are not in the ideal one. We are in here. Some signal leaking from here. Leak. What does leak mean? Leak means DC can come through here. Not only AC, DC can come through here. It's not good, the leakage. And when the AC signal pass here, go over here, it's supposed exactly go into the our amplifier. But because this ESR and this capacitor, the reactant, they both are related to the frequency. And that ESR thing, it makes some the voltage drop in here. If it drops some voltage, then our amplifier inside here, for instance here, is our input transistor, right? Listen, here is our input transistor. Now we do have a capacitor here. Yep, we have a resistor here. Now the signal coming in here is supposed to be exactly the same signal get into this transistor. But somehow this thing is something like a relay to frequency, right? related to frequency. If the frequency up and down, this ESR is changing. And this ESR changing. You see this ESR and this one, they have a ratio. The signal have some voltage drop from here. So if this thing is based on the frequency changing, then the voltage drop in the ESR is different. And what that means to us? Say we feed a signal into that, and then this guy is just acting like a gap, over there. Somebody just switched the door, open wider, narrow, wider, narrow, and then your signal pass here, get into the amplifier, will be frequency related. That's not what we want. We don't want that. So that's why in a lot of amplifiers, in the signal path, they always say you need a good capacitor and with a very flat responding to the frequency and not changed by the temperature or whatever. Even there is many old amplifiers that have a funnel input. The same connect to the turntable. That section have a very small signal input. So in that area, any capacitor in the signal path, it has to be very little leakage and with very good frequency responding and very good temperature stability to be able to work in a good amplifier. Let's do a little test for the old capacitor. I got a 50 volt 4.7 microfarad. K ESR is supposed to be tested in 1000 kHz. We don't worry about the capacitance. The ESR is 2.07 ohm. We got a new capacitor. 50 volt 4.7 microfarad. Actually, it's this one. The one I got, Panasonic 50 volt 4.7 microfarad. Let's see the reading. Same on the 1000 kHz. Whoa, you only got 0.2 ohm ESR. It's much lower. This one's 25 volt 4.7 microfarad. Reading 1.46 ohm for ESR. New one, 25 volt 4.7 microfarad. It's still in the package. We get the reading 2.28 microfarad.